Welcome to today's podcast. In today's session, we have with us an expert from a field related to batteries. Ramesh Natarajan, a veteran with over 42 years of hands-on battery industry experience, will be asking our esteemed guest a host of technical questions. Hope you find this podcast useful to your business. Enjoy the session.
Hello and welcome to this episode of my podcast. In today's episode, I have with me Dr. Carter Abney, who works for Borregard USA as a technical applications manager. Borregard is a company making a crucial paste additive that is used to make the negative plates of lead-acid batteries. Dr. Carter Abney earned his BS degrees in chemistry and theoretical mathematics from the University of Wisconsin. In 2007, he graduated from the University of North Carolina with an MS in chemistry. He worked as an analytical R&D scientist at the Center for Disease Control and Prevention. In 2015, he earned a PhD in inorganic chemistry from the University of Chicago. He worked at the Oak Ridge National Laboratory, ExxonMobil Research and Engineering Company, before he joined Borregard in USA. Dr. Carter Abney has published over 50 peer-reviewed journal articles. He has filed more than 14 patents and patent applications. He has received numerous awards and recognitions for innovative work. Welcome, Dr. Carter Abney.
Thank you. It's a pleasure to be here.
Yeah, thank you so much for agreeing to come on my podcast episode. I have a few questions for you on the different types of Vanisperse that Borregard sells to the lead-acid battery manufacturers, and I'm also keen to know about the new product launched by Borregard, about which you spoke extensively in the Power On conference yesterday. Now, before I start asking my queries, do you have anything more to add, or do you want to say anything before I start the conversation?
I think it's probably worth just saying a few words about who Borregard is and our values and the role that we play in the battery market. So Borregard is a biopolymer company. We harvest Norwegian spruce and sugar maple and loblolly pine and process that into different products in different application spaces, of which batteries is one of them. We're approximately 94% efficient in our processing. So for every 1,000 kilograms of wood that we harvest, 940 kilograms of product come out on the other end. So we pride ourselves on sustainability, and we use science-based targets to reducing our emissions, and that's truly a core part of our company's culture. As far as batteries go, we have also, in addition to the world's most advanced biorefinery, we are the most integrated biorefinery. And so the entire upstream and downstream processes for preparing these lignosulphonates are controlled within our company. So if there are any changes that need to be made for improving product consistency, we have all of the agency necessary to do that. And that's one of the key points that really differentiates us from the other biopolymers that are available for lead batteries. In putting the lignosulfonate in the lead battery, what you end up realizing is an improved capacity and better cold crank performance and substantially improved battery lifetime. And so that's the critical role that we play in the lead battery market.
Okay, and which means that you have a lot of products other than what you do for the lead-acid battery market also?
We have over 800 different products that we sell.
Different products.
Into areas ranging from feed pelleting to agricultural and macronutrient fixation. We have products for oil well and geothermal well drilling, and batteries is one of our main products, one of our core competencies. But yes, we have a wide range of product slates and a number of application scientists.
I know. Ever since I started in batteries, we've been using Borregard. So it's almost 45 years back I entered the industry, and I know Borregard has been quite a popular vendor for the battery industry. Can you tell the listeners the names of the various products available with Borregard, especially for the lead-acid battery industry?
Sure. In the lead-acid battery market, probably the product that customers are most familiar with is Vanisperse A.
Yes.
That's the kind of the industry standard, and as you mentioned, it's been around for decades. You really can't go wrong with it. It's very consistent, high-quality lignosulfonate, and delivers very impressive cold crank performance. More recent developments include Vanisperse HT1. The HT stands for high temperature because the intended application space is high temperature applications. You compromise a little bit on your cold crank performance, but we see roughly 25 to 30% improvement in battery lifetime when using Vanisperse HT1 at temperatures up to 75 Celsius. One of our newer products is Vanisperse DCA. As battery technologies have advanced and there's been a greater need for things like rapid charge acceptance, Vanisperse DCA was formulated specifically to enable rapid charge recovery. And as validated by independent third parties like Argonne National Laboratory, they see that the charge acceptance of Vanisperse DCA is superior to Vanisperse A. And very excitingly, this particular product also maintains much of the cold crank performance that we see in Vanisperse A as well. So it's truly well situated for these micro-hybrid vehicles that have the start-stop feature, and really anywhere that you need to recover your charge quickly.
So for the EFB batteries and all that?
It would work very well, yeah.
Okay. Now when you talk of DCA, does it also have the properties of the high temperature? Is it also suitable for tropical climates as much as it is for a temperate climate?
I think it would work well. So the high temperature performance remains something that our company is investigating further, and so I don't have as much data on this as I would like. But the data that I do have does support strong high temperature performance.
Okay. Now, you have already told me the significant differences between Vanisperse A, HT1 and DCA. Now I wanted to, that DCA is of course for the dynamic charge acceptance, right? Okay. Now I wanted to know whether these are individually meant for different applications of batteries. Like now when you take Vanisperse A, is it something mainly for the automotive segment, or is it also okay for a standby application, or also okay for a deep cycling application? Or do you say that you use Vanisperse A for automotive, Vanisperse HT is for deep cycling application, and your Vanisperse DCA is for EFB, something like that? Have you segmented the product with the application?
So we, when we design our lignosulfonate expanders, we do try to target certain application spaces. So Vanisperse A has been around for a very long time, and it's very reliable. And to be very honest, it will work in any application space. The catch is the people that are developing the battery need to test the dosage and what carbon they're putting in and really optimize for that type of cycle lifetime. But we've seen batteries with Vanisperse A that do very well with deep discharge, even down to 100% depth of discharge. They have very good cycle life compared to other batteries. Vanisperse HT1 was designed primarily for those high temperature applications, and there we were thinking automotive principally, but there are other application spaces that endure high temperature, and it would work well there as well. For Vanisperse DCA, again, we were very focused on the EFB batteries, the micro-hybrid applications, but we also know that all of these expanders find use in things like e-bike batteries. They would work well in e-rickshaw batteries. They work for data centers and UPS. A lot more has to do with how the battery is engineered and designed than the expander itself in terms of which is going to work best. And so that's very much up to the customer.
So it's up to the battery manufacturer to decide. You have a range of products, but you're sure that Vanisperse A is most suited for all applications.
It's a good place to start.
It's a good place to start. Okay,
and put differently, if the choice is between Vanisperse A and other organics like humates or craft lignin, Vanisperse A consistently outperforms these other expanders. And then beyond that, we can make recommendations, and our other products will perform better under certain conditions. But the biggest difference then is going to be what the battery manufacturer does.
Okay. Now, in India, I've seen that some battery manufacturers mix Vanisperse A and Vanisperse HT1, and then they use the combination, the mixed thing. So, do you think such a mixing is okay, acceptable to you? In the sense that, have you done any trials of such a mixture and then usage? And in case you have any experience, can you share or can you recommend how this mixing should be done, whether it's okay, not okay, and if it has to be done, how it has to be done?
So blends are actually very popular in the battery industries, and I know of several major companies that are blending different lignosulphonates to obtain the performance profile that they're looking for. In identifying what one wants for a blend, again, it really comes back to the end application that they want to target. So Vanisperse A and Vanisperse HT1 are very interesting because, while I can't get too deep into the technical details of how we manufacture them, these two products, branch off from our feedstock very early on, and so they have significantly different physical properties in terms of things like molecular weight and amount of sulfur, and those we know have an influence on the resulting battery performance. So when you blend them, you'll end up with kind of different characteristics that one needs to be cautious of. It's pretty well understood that when forming a battery, the temperature should only, it should be as warm as possible and as cool as necessary to avoid drawbacks in performance. With Vanisperse A, we know that temperature really shouldn't get much above 40 degrees Celsius, whereas we have reports from certain customers that they can use Vanisperse HT1 and form their batteries at temperatures up to 60 degrees Celsius, and some even claim to be able to go higher. At the same time, we know that Vanisperse HT1 can get, in essence, foamed or blown out of the electrode if there's too much gassing. It will concentrate at the interface of those gas bubbles in the water, and it will bubble to the surface of the electrolyte. And so one just needs to be very cautious in how they're treating these batteries during their formation processes in particular. That said, we have other customers that will blend in a little bit of Vanisperse A with other products, with craft or with even with wood flour, and what they'll see there is that the intermittency or the inconsistency of these other products can be mitigated by adding the Vanisperse A. They know that they'll be able to reach at least the minimum warranty time by adding the Vanisperse A, and then if the other products work well, it will extend the life or deliver some other improvement in performance. So there are opportunities for blending, but again, it really comes back to what they're trying to achieve or what they're trying to avoid.
So, have you done any trials by blending?
So we've done limited trials. For our part, we form and cycle all of our batteries very consistently, and so what we see is just kind of the averaging of the performance. And so if we have a 25% Vanisperse A, 75% HT1 blend, what we see is really the linear combination of the performance that we'd expect from the pure version of those two batteries. So it really, the benefits from blending seem to be more related to how one is preparing the battery and what one is trying to avoid than the actual performance that they realize afterwards.
From what I understand, I realize it's better to go with hunt rather than blending. That's what I understand after listening to you, because you say that the molecular weight also varies and the characteristics of all these are clearly different.
So I generally recommend only going with one.
Going with one.
But I also acknowledge that there are a lot of customers that will blend it.
And they are successful.
And they're very successful with it. So,
okay. So, I mean, some trials have to be done at the manufacturer's end.
Absolutely.
They have to come and decide what blend suits them.
There is no substitute for testing.
Yeah, of course,
Yeah.
yes. That is always there. Does the solubility of different Vanisperse types, do they vary? And is miscibility also found to be different type-wise? When I talk about miscibility, I'm saying, okay, you mix Vanisperse A in a dry condition. When it comes to HT1, you mix it with water and then put it in the paste, or the other way around. Is there something like that, or what you recommend, or do you think that it's okay to mix everything with water and put it into the paste?
Right. So, great question. There are differences in acid solubility for our different products. In neutral water or slightly basic water, everything dissolves very readily, very quickly. But as one increases the acid concentration or decreases that pH, we know that our products like Vanisperse HT1 and Vanisperse DCA will dissolve more readily than Vanisperse A does. It doesn't dissolve well under acidic conditions at all.
Which Vanisperse A?
Vanisperse A.
Is that a disadvantage for Vanisperse A?
So, that's
or is it an advantage for the other two?
That really gets to kind of the cutting edge of what we're trying to understand in battery science right now. So one of our research priorities is to identify where the lignosulfonate goes and how it functions when it's actually in the battery. And so one concept that we're working to explore further is whether we have dissolution of the lignosulfonate from the negative electrode into the electrolyte, and if that's where it needs to be to achieve the performance that we're looking for. So if that's what's happening, then the solubility in different acid strengths is really a key determining factor. However, at the same time, we don't really have any evidence that supports this, so it's just a hypothesis. And what we do know is that both Vanisperse A and these other lignosulfonates, DCA and HT1, they all perform very well. So it's really difficult to say. I mean, whether it's an advantage or not.
Okay, but I don't think anybody mixes this with acid and puts it in any case.
Sure. Yeah.
And from the battery point of view, I would say, I would like to know, is the miscibility almost similar with water?
So, if you just dry mix this powder with your other additives, carbon and barium sulfate, and then mix it with lead, it will perform very well. You'll have no issues, no difficulties. If it can be dissolved in water first, that might be a little bit better. But to be honest, I don't anticipate they would see much difference.
Yeah, most of the people mix it with water because then the dispersion is uniform.
Yep.
Whereas when you put it as a dry mix and you're doing the dry mix being very light in weight, it can go away into the atmosphere.
Sure. Yeah.
So it's very similar to carbon. So, I mean, of course, carbon, they do a dry mix, but Vanisperse, I've seen many of them mix it with water.
And that will work very well. It will dissolve readily.
Well.
Absolutely.
Yeah, it works well. Yeah. Okay, now, and anyway, once the paste is almost done, it's neutral. It's not acidic anymore.
Right.
So I think that's okay.
Yeah.
In cycling batteries, the vent plugs sometimes have a black deposit. I don't know whether you are aware of it. But then the customer comes back saying that there is a black deposit on the underside of the vent plug. Is it possible that this is due to the Vanisperse which has been used?
I wouldn't expect that's the Vanisperse. I can't actually prove one way or the other. And if a customer is willing to send us a sample of this black residue or the vent plug itself, we can certainly do some tests and evaluate what it is. But the coloration, Vanisperse is a brown color. All of them are a brown color. And so a black residue seems less likely than other things in the battery. So.
I would say it's more from the separators where they use the carbon. It's mostly from the polyethylene separators is what we have found. Anyway, I just wanted to know, so it's not possible that it can be Vanisperse because it's brownish, is it?
I mean, if it's brown, then that would make me think it could be.
Okay.
If it's black, I don't think so.
Is it possible that Vanisperse can leach out of the plates due to overcharge or high temperature?
So again, this kind of really gets back to that fundamental understanding that we're trying to pursue in a very active sense in our R&D teams. Vanisperse A is really interesting because at high temperature, it actually has lower solubility than at low temperatures. And so that's fairly uncommon, but it's due to the biopolymer structure that drives that insolubility. Whereas with Vanisperse HT1 and Vanisperse DCA, we actually see higher solubility at higher temperatures as one normally would expect. So then thinking about how at high temperatures we might be losing more, it's a very interesting system to try to think about. I could imagine that more Vanisperse HT1 or DCA would then be pulled out of the negative at high temperature, but I would think that they'd be more likely to remain dissolved in the electrolyte. Whereas with Vanisperse A, I don't think high temperature would pull more of it out of the battery or more out of the electrode. And if it did, I would expect it then to precipitate more quickly as that temperature stayed elevated and if that acid were more concentrated. So at high temperatures, it's just very hard to say. I mean, so what we're doing right now is we're working with some of the national laboratories around the world actually to use inelastic neutron scattering to monitor the concentration of our lignin in our electrodes. And then we can test those at different temperatures and under different cycling conditions. And so it's really kind of cutting edge work that no one has tried before. But when you imagine you have a very small dose of inorganic material that you've dispersed in this very large amount of lead, there really aren't any techniques available where you can really monitor or measure the amount of lignin that's there. We know how much we start with, but as the battery is cycled, we don't know how much remains. So what our process is we're harvesting these grids and we're using neutron scattering to measure the concentration that remains. And from that, and the amount that's in the electrolyte, we can infer what's happening to the organic as we cycle these batteries at different temperatures and conditions.
Now, when you talk of concentration, what sort of concentration in percentage terms would you recommend that should be used by a battery manufacturer? Or to put it the other way, what is, in your experience, is what battery manufacturers use? Or you can specify any range?
Sure. So it really depends on the application and on the region. In Europe, we know that they use generally around 0.25 weight percent on lead oxide, whereas in the United States, it's typically closer to 0.3%. And in China, we hear that customers are using as much as 0.4%. So it really depends. The other thing is that there's a trade-off in battery performance characteristics. So if you want very strong cold crank or discharge, yes, you want more lignosulfonate.
Yes.
Similarly, with battery lifetime, we see that larger doses of lignosulfonate are favorable for extending the battery cycle life. However, if you're really interested in charge acceptance, you want to try to minimize the lignosulfonate. So it really depends on the application that one is targeting.
Now, you say cold cranking, you need more. But why do you say cycling you need more? Because in cycling there's no cold cranking, there's no high current generally which is drawn. So why do you say in cycling also people use more? So
what we see from our testing is that batteries that are made with more lignosulfonates have longer cycle life than batteries that are made without or with smaller dosages. So during the presentations yesterday, I showed a slide where Vanisperse A was dosed at different concentrations, and then the lifetime of that battery was tested. And we saw the battery's longest lifetime occurred when a dosage of 0.35 weight percent Vanisperse A was used, which was higher than what we saw for the maximum performance for cold crank or discharge capacity. So it's purely based off of the the battery testing we've done, and not really grounded in any sort of mechanistic understanding.
Is there a possibility that cycling battery also requires more because probably some Vanisperse is getting out of the electrode during usage? Is that a possibility?
I think that's a very, very reasonable thing to expect.
Because logically, I can't think why you would want more for a cycling battery, especially since Vanisperse as a component is mainly for cold cranking.
Well, yes, but we also see that batteries prepared without any lignosulfonate die very prematurely. And so even the oldest lead batteries, when they were designed with wooden separators, once those separators were replaced with plastic ones, the batteries died very quickly and they had poor performance. So we know the lignosulfonate is essential, both for cold crank and also for lifetime. Now, the idea that one loses lignosulfonate, either through precipitation or decomposition, I think that seems reasonable. I mean, I think that that's what one might expect. And so adding more could explain why that prolongs the battery lifetime.
Possibly. Yeah. So this is one thing which I had discussed earlier with another good friend of mine from the battery industry who is now also an international consultant. So what he said is you add Vanisperse A and he said you use some wood flour because over a period of time this wood flour becomes a lignosulfonate and that's how he said it extends battery life. Any experience you have with wood flour along with Vanisperse?
So we don't work with wood flour, but I have spoken with several customers who say that that's what they prefer to do also. Okay. So, and again, that does, we've spoken about several different concepts, all of which seem to align around that, that general idea. So whether it's a wooden separator that slowly is leaching lignosulfonate into the electrolyte, or wood flour that's slowly decomposing to deliver lignosulfonate,
yes,
or a higher concentration of lignosulfonate, all of these approaches would prolong the amount of time that lignin is available in the battery, and that would make sense that it would extend the battery lifetime then.
Is there a possibility that excess usage can block the pores of the separators or create any problems?
So we do know that there's a maximum performance. As you add too much lignosulfonate, you eventually do start to see a decline in all of your performance testing. So what that's due to, it could be any number of things. I mean, too much could be just increasing the resistance in the battery. It could be blocking, ion transport channels. It could just be dilution of lead. There are many things that are probably combining of lead. So I mean, if your utilization remains the same, but the weight of the electrode is has more lignin in it and less lead, eventually you'll start seeing lower capacity.
But the dilution of lead is probably, anyway, the concentration is very low.
It is very low.
Okay. Now, is it okay to use less Vanisperse in a tropical country like India compared to a cold climate, temperate climate country?
I mean, I think a lot really depends on what one season they're testing. So I would think that you'd want to use probably a similar amount and possibly even a little bit more than temperate.
Tropical climate?
So, I mean, again, coming back to the battery lifetime, I mean, assuming that one wants to make a battery that lasts for a long time, and one is less concerned with the cold crank performance, having more lignosulfonate will extend the battery lifetime. And that should be true at high temperatures or low temperatures. And in fact, with HT1, the data that we have shows that a higher dosage of HT1 delivers better, longer battery lifetime than a lower dosage of Vanisperse HT1. So yes, we know that high temperature is very hard on lead batteries and causes them to fail more quickly. and we know that adding more lignosulfonate extends the life. So I would say adding a little bit more with the interest of prolonging the battery lifetime. And I would say that cold crank is less important.
Okay. So anyway, that's a viewpoint, because I was expecting that since the product is made more for CCA, you may probably say that in tropical it's okay to use a bit less. That's what.
Well, I mean, I think some important things to remember here are first that I'm selling lignin. So, I mean, that's
so deviating, taking this opportunity, now deviating a bit from the pure technical questions.
Well, but I would still emphasize that the cold crank performance, I see the cold crank performance as a benefit, but not necessarily the reason to put the lignosulfonate in. You can get good cold crank performance from any number of different organics. It's the battery lifetime that really is the advantage of the Vanisperse product line.
So now, since we got out of into a commercial, I just wanted to know, India's exports have grown recently. Now, deviating a bit from the technical questions, I wanted to know, is it that you're selling more in India and Asian countries, or are the sales good in Europe, US, and how's the market like?
Sure. So, to be honest, I'm less focused on the market than I am on the technical side of things. What I can say is that in terms of volume of sales on a country basis, our largest sales go to China, second most go to the U.S., and India is the third most region for sales. Very strong sales across the board. It's been a very positive market for a long time, and the forecasts we're seeing suggest that it's going to remain strong for a long time. I would also speculate that just kind of with the different companies that are growing in the area of Southeast Asia, India, through the kind of the South Pacific into China, I think that the future is very bright here. I'd expect to see very strong growth going forward, and it's a very exciting time. That said, our strategic distributor in India is Harsha Industries, and they would certainly be able to answer that question a little bit more completely than I can.
So I have to ask Mr. Harshpal.
Ask Mr. Harsha, yes.
Of Harsha Industries.
Yes.
Okay. They are your main distributors in India?
Correct.
The sole distributor, is it?
So we do sell some other lignosulfonates to different distributors, but they are our primary and preferred distributor.
Harsha Industries.
Correct.
Okay. Now, you also make for lithium ion, right?
Correct. Yes. We've just launched a product called Vanisperse LI, which works by dispersing carbon and graphite in lithium ion battery slurries. And that what that does is several favorable things for lithium ion electrodes. First, it prevents agglomeration of carbon and graphite particles, which gives you a more stable and smooth cast surface. The other thing that it does is it prevents this phenomenon called particle jamming, where you're trying to put different sized particles through your slot decoder too quickly. And particle jamming results in bubble formation and poor adhesion to the electrode and an uneven surface. And so what it does is it kind of lowers the amount of development time required and increases the throughput that you can run your coating line at. At the same time, you can reduce the amount of water usage in your slurries and decrease your drying time, all of which aids in the battery manufacturer's efficiency and cost savings.
Okay. Now, there was one more product which you talked about yesterday in the conference, which is some new product. That is for lead acid, right?
Right. So that's Exilva. So it's a new product. Exilva. Yep. Launched by Borregard. And what it is when you think back to what we can do with wood, there's two main components. Oversimplifying things grossly here, but wood is made up primarily of your lignin and your cellulose. And so up to this point, we've spoken only about the things that we do with the lignin fraction of the tree. But the cellulose is also valuable, and when fibrillates that cellulose, that's what you get that becomes exsilva. And so it's got a large number of very kind of fine polymer lengths extending from the cellulose backbone. And what that does is it disperses readily in water, and those entangle with one another, adding different mechanical properties to the final product. So when we put this into our negative electrodes, we did mechanical testing and saw that it was 30% stronger than the control electrode that just had Vanisperse A in it. Well, it had no negative performance impacts or rheological impacts to making that battery.
Since you say it's cellulose, it must be probably having some effect like glue.
Very much. Yep.
Very much like glue.
Yeah. Yep.
Okay. Now, does this have to be added in addition to the Vanisperse quantity, or you can reduce the Vanisperse and use this?
To be honest, we haven't looked to see if it allows us to reduce the amount of Vanisperse. It's still relatively early in terms of our development,
okay.
But
does it cost too much? Excellent.
So to be honest, I really don't know much about the pricing.
Okay.
Again, I'm on the technical side, and so
no, I just wanted, because the listeners would like to know if they have to use something else, then what's the cost implication?
Sure.
So I just asked you.
Yeah.
It's okay. So thank you very much, Dr. Carter Abney. It's been a pleasure talking to you, and I'm sure our listeners will benefit a lot after listening to you.
Well, thank
you very much.
And thank you for the invitation. It's been absolutely a pleasure to be here and to be on your podcast. So
thank you. Thank you.
Thank you.
Please do visit www.rameshnatrajan.in. Keep yourself updated about our new releases by hitting the subscribe button.